Hello everyone, this is the second numerical on equivalent static method for determination of the lateral forces coming on the structure. So here the numerical goes. Consider a 4-story reinforced concrete office building. So we know that it is an office building. This helps us to know about the importance factor of the structure. It is a reinforced concrete building as shown in the figure. The building is located in Shillong. So seismic zone 5 he has already mentioned in the question. If zone 5 is not given over here, you have to look into the chart and identify Shillong belongs to which zone. The soil conditions are medium to stiff and the entire building is supported on a raft foundation. The RC frames are infilled with brick masonry. So the frames are infilled with brick masonry. So there is brick masonry walls. The lumped mass due to dead loads is 12 kilonewton per meter square on the floors and 10 kilonewton per meter square on the roof. So this is the dead load coming on the floor and the roof. And there is live load also present. So on the floors are to cater a live load of 4 kilonewton per meter square and 1.5 kilonewton per meter square on the roof. So it's very clear on the roof we have got a lesser amount of load and on the floors we have higher amount of live load. Determine the design seismic load on the structure as per the new code. This particular example here is solved and we will there must be some corrections. It is of old code, so I'll be telling the corrections. You all can solve the numerical. This goes the plan x direction and y direction. In the x direction there are 4 bays, 1 2 3 4, each of spacing 5000 mm. It is understood that is 4 number of bays at 5000 mm. So this center to center spacing is 5 meter. In the y direction there are 3 bays, 1 2 3 at 5000 again. So A, B, C, D they have named 1, 2, 3, 4, 5 in x direction. This is the elevation, that is the ground story is 4.2 meters. First story is 3.2, second story 3.2, and the last one is also 3.2, something similar to our previous example. So coming to the solution, for seismic zone 5, the zone factor is 0.36. So what we can do here is we will take up the book also and let us check the code book. So zone 5, the seismic coefficient is 0.36. What else do we require from the code book? That is, apart from the zone factor Z, we will be using the response reduction factor and the importance factor. So here table number 8 gives me the importance factor for various kinds of buildings. So as is an office building, so here if I look into this very carefully, residential or commercial buildings other than those listed in 1 is 1.2. Any of the office building I can take it as 1.2, or 1.5 is for buildings like critical governance building, school, or monument buildings, and hospital, telephone exchange, television station, etc. So what we can do, any office I cannot list it under this, so I will go it under a commercial building, importance factor 1.2, and the response reduction factor. So as is a moment resisting frame with it's an RCC with masonry infill. So we'll get back to this again, and we require table 10 for the load calculation. Okay, so we will be picking up the load from this particular percentage has to be added up. So going back to our numerical now. First, he says for seismic zone 5, the zone factor is 0.36. Yes, we have already identified. Being an office building, the importance factor I is 1, he says. We will consider it to be, we will take the importance factor to be 1.2. Okay. Then building is required to provide resisting frame. Yes. Hence, the response reduction factor is 5. He's considering it to be a special moment resisting frame, and hence the response factor is 5. So if I look into moment resisting frame in the code book here, so moment resisting frame with ordinary is 3, RC buildings with special moment is 5, steel building and steel. So what we can do, Ours is an RCC building with special moment resisting frame, and so I will go ahead with response reduction factor to be 5. Okay, so getting back to the numerical seismic weights now. Okay, so we know that I have a value of dead weight, that is 12 kilonewton, and for floors and roof, and live load. So first let us calculate the floor area. What is the floor area? Because my weight is given in per meter square, if I'm able to multiply the area to this, I will get the total weight, that is in kilonewtons. So now what we will do, looking into the plan of the building, this is 5, 10, 15, that is 15 meters in y direction, 5, 10, 15, 20 in x direction, correct? So 5, 10, 15 y, 5, 10, 15, 20 in x direction. Total floor area is going to be 15 into 20. So the floor area is 15 into 20, that is 300 meters square. Since the live load is 4 kilonewton only, that is I have to use a clause here for live load from the code book. Now what does the code say is table number 10, the imposed uniformity distribution floor load and percentage. It is up to 3, live load is up to 3 kilonewton per meter square, then I will add 25% extra. Any live load given which is about 3 kilonewton per meter square, extra add total extra percentage of imposed load will be 50%. So in our case, in our current case, they have given us a live load of 4 kilonewton per meter square, which is falls under about 3. So I have to add extra 50% to it. So going back to the numerical, here the calculation is shown here. Since the live load is 4 kilonewton per meter square, that is, it is more than 3, only 50% of the live load is lumped at the floors. At roof, we will never be considering the extra part, that is extra percentage, only at the roof. And the total seismic weight of the floors is calculated as follows. So at each floor level, how many floors are there? 1, 2, 3 roof. So W1, W2, W3, that is 1, 2, 3 floors is your area, total area 15 into 20, 300 meters square, and 12 kilonewton per meter square is given in the numerical. The dead load is 12 kilonewton per meter square. I have to add 50% of live load to it, that is 0.5 of 50% of 4 kilonewton per meter square. That makes it 4200 kilonewton per meter square. When I'm calculating for the roof, I have to consider only the direct load given mentioned in the have to directly mention only the load that is given here. Floors are to cater and roof is 1.5 kilonewton, so I'm going to ignore this. The dead load of the roof is 10 kilonewton per meter square. So what he does is, at the roof, I will calculate the dead load alone, that is 300 into 10. We will not consider the live load at the roof. Now total seismic weight is, there are 3 floors and 1 roof. So 3 into 4200 plus 3000 kilonewton per meter square. So this is the total seismic weight. Now I think the previous example that we have taken, we had directly have got these values of the weights at each floor and at the roof. But if you get a case wherein they are asking you to calculate, this is the methodology how you have to proceed. So the total weight now is going to be, there are 3 floors and 1 roof. I add them sum up, so I get a W, total W, summation W. Then fundamental piece, the resting is provided by moment resting frames infilled with brick masonry. Hence, T value is point. Now, if I want to check this again, I know I have to go to the code book, back to the code book, and we have the formula here for different types of structures. What is the equation given? Okay, so this is your seismic coefficient. I will be picking up for static equivalent method the T from here, and the equations of T are given. This is the loading here, yeah, page number 21. So bare MRF, that is without any masonry infills, and buildings with RC structural walls, or all other type of buildings is over here. So what we are going to do is RCC building we are considering. If I look into our problem statement again, this that is for other buildings 0.09h divided by root of d, right? That is for other types of buildings. He is considering it to be this formula. All other buildings where T is 0.09 times h divided by root of d, where d is the base dimension. So we know the base dimensions of the structure. It is 20. X direction. If I'm taking x direction, it is going to be 20. If I'm taking y direction, it is going to be 15. So I'll substitute in this and I'll get the value of t. Substituting the value of t in to get the SA by G, we find the SA by G as follows. Resubstitute back to get the design coefficient, that is Z I by 2R into SA by G. So substitute, you will get a AH value. So base shear is calculated by AH into total width. I know now the AH, design horizontal seismic coefficient, into the total width. I get a base shear. Now for distribution, what we do, the same calculation is also done for y directions also. So T I find out, then based on the natural period T, I will get the value of SA by G from the code book and then calculate AH. This building, for this building, the design seismic weight in y direction is same as that of x. So we'll take y direction only. Now, level weight, story level weight, height from the floor, WHI square divided by summation of that, and x and y. The extra is x and y, and calculate the values. I repeat, this particular example is solved by old code method. I have given you the procedure for the new code method because the page number and table are changing. Not much of changes there, but there are some minute changes. So go through the clauses and page numbers given in the procedure accordingly, and then solve this particular example. Yeah, thank you.